Good evening, this is Miss Dagenford, and I'm redoing these videos because, well, the sound wasn't working too well, so I'm trying this again. We did an introduction to photosynthesis in a previous video. Now we're going to look at the light-dependent reactions. And the light-dependent reactions, as the name implies, this is where you're going to see the light waves. And so let's go ahead and dive in. And we first see a diagram that does not seem to make sense. We have zigzags all over the place. We have little green dots. What in the world's going on? Well, let me show you what's where it actually is occurring. So this would be one of our thylakoid membranes. So if we go all the way back to our beginning, where we did our intro, if you took one of these thylakoid membranes and enlarged it, well, we'd have this diagram. Now, if you wanted to examine the energy levels that's going on, and you took these out of the membrane and kind of plotted them on a graph, this is what you would see. So imagine that this is kind of representing a graph, and we have energy on the y-axis. So this is called the Z scheme for a good reason. Here's our letter Z, and you can see that right here. And the Z scheme represents the transactions that are occurring with energy. So here are the chlorophyll molecules and their reaction centers. Now we have two main reaction centers. One is called photosystem 2, one is called photosystem 1, as you can see. Now, they don't go in order from left to right. Photosystem 1 was discovered first. What I like to think of, just to kind of help me keep it straight, think it's counting down. 3, 2, 1, and then boom, yay, we're done. Now there's no three; it's just two and one, but it goes down, down in the numbers. So what's going on here? Well, all of these little green dots represent chlorophyll molecules, and what they're doing are absorbing the light energy in their electrons, in their electron orbitals. You remember back in chemistry class, the electron orbitals represent the energy states. And so as the chlorophyll molecules are absorbing the light wave energy, the electrons are rising in their energy states, and then they fall back down. And as they fall back down, they're transferring the energy to another chlorophyll. And this kind of bounces around until you get to a pair in the center. They're given the name P680 because that's the wavelength of light that it absorbs. Um, and these chlorophyll molecules are able to take that energy, and the electrons don't drop down. They actually leave the chlorophyll molecule. They exit, they jump out. And as the electrons are raised, and so notice what we're doing here, we're kind of indicating the energy level is going up. And so that, again, going back to the graph. So they go up, they're accepted by a molecule. We just call it an an electron acceptor. And this electron acceptor now has this higher state of energy. Well, sorry, the electron, as the electron falls back in its energy states, that energy can be used to do work. And so we're going down an electron transport chain very similar to our mitochondria. The molecules are a little different. We have plastoquinone, cytochrome, plastocyanin. It's at this middle state that we're going to be able to make ATP in a process that you should recognize. And then you have the first photosystem, which can do the exact same thing, only with a little different wavelength of energy. Light energy is absorbed. The electrons can jump out because they've absorbed that energy, and then they're accepted by that primary electron acceptor. We get another electron transport chain, and this time, we're not making ATP. We're going to pass it to ferredoxin. Ferredoxin is going to pass it on to a molecule that accepts those electrons, we have a NAD plus, and as they accept the electrons, this becomes NADPH. Somewhat similar to NADH, very similar in fact, and in fact it has the same job. It's going to ferry, just like a little truck, it's going to ferry our electrons over to another spot. Should be ringing some bells here with our cell respiration. NADH and FADH2 back in the Krebs cycle and electron transport chain. So we've made two processes, ATP and NADPH. Now we have missed something. Let's go back. When a chlorophyll loses that electron, you're not going to be able to pass another electron. It's just not going to happen. So we need a replacement source of electrons, and that replacement source comes from water. So here's our water molecule. It gets split. An enzyme is there to split. And we get two electrons that become that replacement source for the chlorophyll. And then we are left with, and just to keep this balanced, you take four water molecules, split them, we get electrons. We're going to get hydrogens, which are kind of interesting. What's going to happen to them? And then we're left with O2, which leaves as a wasteful gas. So that's our linear electron flow. A lot of plants will have this happen. Some, and here we can real quickly fill these out. So what's the product of photosystem 1? Remember, that's the one kind of ending it, NADPH. What's the product of photosystem 2? ATP. And of course, you can also say oxygen, but we're not worried about that right now. That's just leaving the plant. And then what reaction is happening to cause oxygen? That's water splitting. Yay. Um, Now, bacteria also have some of these thylakoid-like membranes. Remember, they're prokaryotic, so what we see is the outer membrane of the bacteria kind of curving in similar to thylakoids. What they do is a cyclic electron flow. They only have photosystem 1, so that was the one first discovered. Light energy is absorbed. Instead of transferring it to an NADPH, it goes back. Ferredoxin shuttles it to cytochrome, and you're going to make ATP from that. So that was our first photosystem to be discovered. We understood that bacteria are doing something interesting here. They're cycling this back and forth. We don't see the photosystem 2 involved in this process. So that's we're going to come back to this chart. So that's it as a schematic. This is what it actually looks like in the process. So what's interesting, now we can put together what's going to happen in the center part. Here's our photosystem 2, and the energy in that excited electron is going to be used to actively transport hydrogen ions. Now I'm hoping that this is again setting off bells. Um, as you remember, this is happening in the mitochondria as well, only in a different spot. So that first electron transport chain is going to be shuttling hydrogen ions or protons inside, actively transporting, using that energy in that electron. And then as they pile up, we're getting a high concentration of those protons. They can leave, they can diffuse through the ATP synthase, generate ATP, yay. And then together with the first photosystem, we're going to generate our NADPH. So those are our two really important products from our light independent reaction. And we'll see what happens to them next in our Calvin cycle.